Okay, today we're going to continue talking about the bipolar junction transistor, or BJT. We're going to specifically talk about the modes of operation. Modes of operation are set by the bias point. Specifically, we talked about whether the junction was forward biased or reverse biased. So we're going to examine a case where both of the junctions are reverse biased. So we're going to set VBE as less than 0 volts and VBC as less than 0 volts. Now, when this occurs, we end up having two depletion regions that are formed. And this happens because free carriers that are in the different regions of the device end up being bound to one another at the surface. So we have holes coming up to the surface from the N-type material in the emitter. We have electrons coming from the P-type material in the base. These carriers get bound to one another, and they effectively can't move, and so they form what we call depletion regions. Now, this also happens at the interface between the base and the collector. I should note that this is the emitter region here, the base region here, and the collector region here. And when we have these areas where carriers can't move because they're bound to one another, effectively we form an insulator. And so we have some semiconductor material that's doped, separated by an insulator, and then some more doped semiconductor material. And that leads to depletion capacitances. The depletion capacitance between the base and collector junction is called C mu, and the depletion capacitance between the base and emitter junction is called C pi. And we can change the width of the depletion regions by changing the size of the reverse bias, and hence we can create a voltage variable capacitance. Now, this mode where no current can flow is called cutoff. And we use this when we're using the device as a switch primarily. I should note that for a PNP transistor, if we just reverse the order of the subscript, the same thing holds true. So for VEB less than 0 and for VCB less than 0, we have a PNP in cutoff. All right, so now let's examine another useful case. All right, so here we're going to set VBE greater than 0 and VBC less than 0. So in other words, the base to emitter junction is forward biased and the base to collector junction is reverse biased. Now we have electrons that are in the emitter, and because they're energized, they're going to start to travel and they'll diffuse across the base junction, and most of them will continue on towards the collector. Now this makes sense. The emitter is emitting the electron and they're being collected by the collector. Now, at the same time, we also have holes from the base diffusing across the base to emitter junction. And some of the electrons end up getting bound by these holes, and this looks like a current of electrons flowing out of the base. Now, we reference current differently. So if we have electrons flowing in one direction, we tend to say that we have a positive current flowing in the other direction. And so we say that our collector current IC is flowing from the collector to the emitter. And our base current IB would be flowing into the base. For a PNP, the operation is exactly the opposite. We would do the analysis, but we would say that we have holes that are diffusing in this direction, and all the other arrows would remain true. And since holes are moving in that direction, it would also mean that the current would be flowing in that direction because the hole has a positive charge. All right, for the PNP transistor, we reverse the order of the subscript and we say that VEB is greater than 0 and VCB is less than 0 in order for this operation to occur. Now, we call this mode of operation the forward active region, or we'll abbreviate this as FAR for forward active region. Now, in the forward active region, the transistor behaves like an amplifier. And what we mean by that is the transistor is going to behave like a voltage variable current source. So we can say that the collector current, IC, is equal to IS times E to the VBE over VT, where VBE is the voltage that we apply to the base emitter junction. VT is the thermal voltage, and the thermal voltage, you might remember, is equal to KT over Q. Or for this class, we're going to say that this is equal to 25 millivolts. And IS is the saturation current of the device, and it's dependent upon how the device is doped and the geometry of the device. Now, we also know in the forward active region that the device has a beta, which is the current gain. This is equal to IC over IB. This is typically on the order of 100. And there's also a term called alpha, which is equal to beta forward over 1 plus beta forward. And this should be pretty close to 1. And then we also note that the emitter current is equal to the sum of the collector current plus the base current. And with these things, we can find out all of the operating characteristics of the device that we're going to use in order to find the small signal performance. All right, so before we find the small signal performance, we need to find the device's bias point. And this is the DC point that we're going to set the device to operate in on average. We're going to care about the DC currents flowing in the device, the base current, the collector current, and the emitter current. We note for our NPN, the currents flow in the direction that I've just drawn. For our PNP, the direction of the current will be the opposite. Nonetheless, we can draw our curves the same as before, just noting that we're looking at a different direction. All right, so we sweep the collector to emitter voltage of a transistor while applying different base to emitter voltages, and we get a family of curves like these gray curves that I've drawn here. We have a couple of familiar regions of operation. So our first region is when no current is flowing, and this is the region that we call cutoff. And we have a dividing line between when the curves become flat and when the curves are still changing dramatically. And that dividing line separates the region between saturation and the forward active region. And generally, we say that we apply an approximation and just say that the device enters saturation at some constant voltage. And oftentimes we'll say that VCE, saturation, is equal to 200 millivolts. But you'll note that that is an approximation that we use. And we like to operate the device at a specific point. We call this point the Q point, and that is a specific combination of voltages and currents. So the Q point, it will have a VCE Q, an IC Q, and a VBE Q that the device operates at. Now, all we have to do is reverse the subscripts when we're describing the operation of the PNP transistor, and we see the same characteristic. So in order to find our bias point or our Q point, which is the DC voltage and current around which there will be a small signal voltage and current swings, those are our AC signals, we do a couple of things. So one, we assume the forward active region. This allows us to use the current expressions that we found on the prior page. Once we assume that, we'll use KVL around the base to emitter loop. And doing this allows us to assume that the base to emitter is a relatively constant voltage. And for this class, we'll generally assume that VBE is equal to 0.7 volts, unless we're given clues that it might not be, such as we might be given a different saturation current and a different VBE, and we can try and find out what the actual VBE is. And then finally, after we do this KVL, we're going to do some checks. So we're going to do KVL around the base to collector loop. And we're going to check to see if the collector to emitter voltage is greater than VCE sat. And if it is, and all the currents check out from the prior KVL analysis, then we can assume that the device is in the forward active region, and that the assumptions that we made are correct. If it's not, we need to rebias the device and check again. All right, so we're going to stop there, and in the next set of slides, we're going to look at the small signal model. We're going to derive the small signal model from the DC values that we found from our Q point.